counting, but it's like a new chapter, so we're going to call it a new unit, but it's really like all just more counting. I think this is just something that Euler decided one day he was going to investigate, and next thing you know, it became a whole math branch. Okay, good. Okay, how many ways are there to express the number 1 as the sum of a bunch of positive integers? Just one way. That's kind of boring. Okay. How many ways are there to express 2 as the sum of 2 integers? 2 ways. You could just go like 2, or you could go like 1 plus 1. Agreed? Okay, good. Let's keep going. This is fun. How many ways are there to express 3 as the sum of a bunch of positive integers? We can do just 3. We can do 2 plus 1. We can do 1 plus 1 plus 1. Oh, and by the way, when I say number of ways, like I mean like actual different number of ways, like commutativity and associativity, like whatever. Okay, good. Cool. La la la. Okay, let's do one more. 4 is well, let's see. What do we got? You can do 4, or you can do 3 plus 1, or you can do 2 plus 2, or you can do 2 plus 1 plus 1, or you can do 1 plus 1 plus 1 plus 1. I feel like that's it. Yeah. Okay. So let P of n be the number of ways to partition and partition. Okay, well, so we want to figure out a formula for this. And oh, by the way, there's an obvious combinatorial significance to this. You can easily turn this into like a story, which is, I don't even know. How many ways can you like distribute, you know, if you have like 4 candy bars and you are going to split up your largesse into some small groups. How many ways loosely are there to do that, right? You could give all your candy bars to just one person. You could give 3 to one person and 1 to another. You could do 2, etc. Cool. So yeah, it's kind of a number of ways to partition is also a number of ways to divide up some quantity of things that you have. Okay. Well, all right. Now some analysis. And there's 2 things. Yeah. Are we gonna do this? Sure. So we think of this as this is like I'm gonna say I have like 1 here.
No, I do 1.
And here I have 1, 2, or I have 2 1s. And or is kind of like addition or something. So I'll just write plus and then I'll write like or. Oh, interesting. How about 3? How many ways are there? Or I'm just being a little big necessarily. I'll just keep talking. So here I can do like I can do 1 3, or I can do 1 2 and 1 1, and I kind of like just call that like multiplication-ish because it's like and or something. Plus 3 1s. So has everyone got the verbal connection? Even if you don't understand exactly what this all means? Okay. So what I see here is that these are kind of acting like exponents or something. This is like an or, this is like an or, this was like in kind of an and here, and all these things were sort of like ands. And so yeah. Let's do one more row. Here, the 4 1. What are all the ways to get 4? I can have 1 4. Or I can have 1 3 and 1 1, or I can have 2 2s, oops, plus, or I can have 2 2s, or I can have 1 2 and 2 1s, or I can have 4 1s. And so each of these like 5 different ways of doing it are kind of like the 5 ways that that you could make some exponents add up to 4. In other words, think of this. This is kind of like z. If you sort of convert this into like a polynomial, this is like z to the 1 times 4. This is like z to the 1 times 3 times z to the 1 times 1. This is z to the 2 times 2. This is z to the 1 times 2 times z to the 2 times 1 plus z to the 4 times 1. So, if you basically, what I'm saying is, consider all conceivable like products, and anytime they turn out to be z to the 4th, however many of those you have, and here you have 5, is going to count the number. And so, basically, there's some sort of polynomial out there which will do this. So let's do the 5 case. So what are all the ways to do 5? So you know, in practice, if the numbers are small enough, it's faster to just do it. So we can do 5. We can do 5 as 5. We can do 5 as 4 plus 1. We can do 5 as 3 plus 2. We can do 5 as I don't know what's left. 3 plus 1 plus 1. 3 plus no. 2 plus 2 plus 1, 2 plus 1 plus 1 plus 1, and just 1 plus 1 plus 1 plus 1 plus 1. I count 7. Okay. Well, that number 7 can be thought of as like the coefficient of some sort of like weird infinite polynomial out there that's like z to the let's do it directly this time. So z to the, I have 1, 5. Here I have z to the, I have 1, 4, and 1, 1. Why am I doing this?
Well, like, I feel like when you have 2, 2, I feel like you should be being z squared times z squared. Not like, I feel like the way you write it is weird and unclear. Like, I don't know why you're doing multiplication inside the exponent.
That's your fault.
Because like, how is z to the 1 times 4 different than z to the 2 times 2? Like, how are you making that? I just don't know where you're making your distinctions.
Yeah.
Like, you should be writing z squared times z squared, and like z cubed times z, and like z times z squared.
Does it make sense to you?
Yes.
Okay. So wait, I guess the idea here, well, maybe we just cut to the end. The end is, what we do is we just construct an infinite polynomial. This is like a generating function. Have you seen this before? Wow.
We kind of investigated in 8th grade, or like when I was in 7th grade, he was in 8th grade. We thought we were really cool, but we weren't.
Cool. Good. Yeah. So, okay, we'll watch. Here's what we do. Consider the following infinite polynomial. 1 plus, and now all the powers of z. But here's what I'm going to write this as: z to the 1 times 1 plus z to the 2 times 1 plus z to the 3 times 1 plus z to the 4 times 1. I'm going to go up one more, z to the 5 times 1. And this goes on and on forever. So this is just an infinite polynomial with increasing powers of z. All right, take that infinite polynomial and multiply it by another infinite polynomial. This one's skipping by 2's. So now we go z to the 1 times 2 plus z to the 2 times 2 plus z to the 3 times 2 plus z to the 4 times 2, etc. So now we're going, 2, 4, 6, 8. And this is also an infinite polynomial. While you're at it, keep multiplying by, and you just do this forever. 1 plus z to the 1 times 3 plus z to the 2 times 3 plus z to the 3 times 3. Now we're skipping by 3's. 1 plus z to the 1 times 4 plus z to the 2 times 4 plus z to the 3 times 4, etc. And and 1 plus z to the 1 times 5 plus z to the 2 times 5, and then this goes on, and then just like on and on and on forever. Alright, now imagine multiplying this infinite polynomial out, fully expanded. If you do that, you're going to have only a certain number of z of terms whose exponents add to 5. What are all the possible ways I can do it? So maybe start with this 1. Is there any way if I take the 1 from this first one for me to get an exponent which adds to 5? Yeah, I would have to do 1 and then z to the 5th. That one there, right? What's up? I think that's the only way, right?
Could you get 1 z squared, z cubed, and then all other ones?
No, but if I'm doing...
He's saying,
Oh, okay, I guess you're right. Yeah. So you have to do... Wait. Well, I was thinking there's no way to just 1. Okay. What are all the ways? Just name a way that we can end up with an exponent of 5. Name a way.
z to the 5 times 1 times 1 times 1.
Yeah. One way is we take a 1 from the first one. We take a 1 from the next one. We take a 1 from the next one. We take a 1 from the next one, and then we take this z to the 1 times 5, and then we take 1s thereafter. Okay, forever. That will give me 1. Okay, I'm going to not write 1s anymore because that's annoying. Okay, that's one way to do it. What's another way to do it? Suppose I grab this first z. So that's z to the 1 times 1. Well, if I have a z, now the rest is just going to be the number of ways to get 4.
Wait, sorry, how are you saying this is, was it commutative or something?
Well, at the moment it's just a polynomial.
Okay.
So I mean, you can almost ignore the original partition displacement. So I grab z to the 1 times 1. What's left?
So you can do,
If you have 1, you could get like, maybe like, well, I have to almost now take, wait a second. I can go here.
yeah, dude.
That works, yeah. So I have 2 2s. And now the rest will be 1s, right? So I took this one, and I took this one, and now the rest will all be 1s, because I already have my 5s. Okay, what's another way?
1 times z squared, z to the 1 times 2 times z to the 1 times 3 times all 1s.
Yeah, so, yeah, I could grab that one, which gives me 2 already. Now I've sort of passed out 2 candy bars. And now I must grab a 3. This is the last time a 3 appears anywhere in this infinite polynomial. So I have z to the 1 times 3. Okay, plus, what's another way to get 5?
Like that, but do it like 3 times. Like the first term and then do it 3 times.
What first term?
Z to the 1 times 3 and then pick 2 other, like z to the 1 times 1 and then 1 other one.
No, but that doesn't appear
z to the
anymore.
3 times 1 times z to the 1 times 2.
Z to the 3 times 1.
Yeah, and z to the 1 times 2.
I could grab that 3, and then I would grab,
Z to the 1 times 2.
yeah, that one there. How else can I do it? 1, 2, 3, 4. I think there must be like 3 more.
Z to the 5 times 1.
Yeah, I could just grab that one right there, and then it would be done.
Oh, I'm being
1,
stupid.
2, 3,
Yeah,
4,
okay.
5. 2 more. Can I do 4? No, I can't. I have to do, let's see. Well, I can just
You
look
do
at my
z to
own
the 1
thing.
times 1.
Did I do 4? I didn't do this one yet.
1 times 1 times 1.
You do 2 times 1, yeah.
No, I can't do 5 ones. I did 5 ones.
Wait,
I
you
did,
can do any of the 4s.
so wait, I did this
Yeah, you do
one.
1 times 1, 1.
I did
1 times 4.
1,
Yeah.
2, and
No, 4 times 1.
Yeah. No, we wrote it as 1 times 1.
Oh, so,
1, 2, 3, 4, 5.
How are you gonna get the other one?
5.
Z to the 1 times 1.
Yeah.
Z
Times 1 times 1 times z to the 1 times 4.
Wait, hold on. Let's finish this because we're running out of time. I lost track of what was going on.
No, take z to the 1 times 1.
That's 1 quarter.
and then multiplied by z to the 1 times 4.
Oh, yeah.
Yeah.
Okay, and there must be one more.
2 times, no,
This one, did I do that one yet? Oh, yeah, I did that one.
times 3. Wait, 1 times
Yeah,
3.
this one and this one. Does that work? No. What the hell happened?
Something 1 times 3 and 2 times 1?
1 times 3 and 2 times 1.
Oh, yeah.
Yeah, so z to the 2 times 1 times z to the 1 times 3.
Testing skills.
Yeah, so, and there's just, we've counted them all. There are no more ways to get powers of z to the 5th. And each of these corresponds to one of the partitions. So, let's go in order. Here we have 1, 5, right? So that's this one. Alternatively, we have 1, 4, and 1, 1. 1, 4, and 1, 1. Here we have 1, 3, and 1, 2. So 1, 3, and 1, 2. Here we have 1, 3, and 2 1s. So 1, 3, and 2 1s. Here we have 2 2s and 1 1. So we have 1, 2, and 3 1s. And finally, we have 5 1s, which is just that one. So the theorem here is that, basically the theorem is that the number of ways that if you take this infinite polynomial out forever and do all possible multiplications, then the coefficient in this infinite polynomial of z to the n counts the number of ways of doing the partition. This is called a generating function. This particular one is like an infinite generating function. A generating function is like some weird sort of like polynomial construction which produces as the coefficients of your polynomial the solution to the problem that you're trying to find. Alright, I was going to do some whole other things. Does this make sense?
I mean, I don't know why.
Like, I guess
Why
you
it
can
works?
multiply
I mean, I know why it works. I don't know how you're going to use it.
Oh, you just write some computer to multiply out polynomials up to like, well, okay. So here's how I would use it.
Yeah, I'm like,
This is not an efficient thing to do, but suppose I wanted to know the number of partitions of 7. It would be much faster to just do it, but suppose I didn't want to do that, I could just generate this polynomial. And if I was going to generate this polynomial, I don't have to actually do it infinitely anymore, because at a certain point you can't get 7. So you would go, what would you do? You'd go 1 to the Bell's ring, 1 plus z squared plus z cubed plus z to the 4th. Picked a bad example, z to the 5th plus z to the 6th plus z to the 7th. And now, on the next one, you go 1 plus z squared plus z to the 4th plus z to the 6th. And now I don't need to go out any further, right? And then you multiply by 1 plus z cubed plus z to the 6th. And then 1 plus z to the 4th times 1 plus z to the 5th times 1 plus, that's it. No, z to the 7th. And now, I see how I sort of truncated? I think I messed up. That should be 5, right? Yeah, I got hopeful. 1 plus z to the 6th and 1 plus z to the 7th. And then I just stop. So I actually don't need an infinite generating polynomial to get P7, because I don't need to list powers of z that can't possibly contribute to my z to 7. You guys with me? So here I went up to 7, here I went up to just under 7, and then etc. And now, were I to multiply out this entire polynomial, which is annoying but not terrible, then whatever the coefficient of z to the 7th is, that would be P7.
wait,
That's the sense in which it's useful. Yeah.
I don't know, I thought that you go in this direction of like the closed form is like 1 over 1 minus z